Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain.
There's a volcano in Russia. Well, there are a lot of volcanoes in Russia. Out on the Kamchatka Peninsula, across from the Bering Sea from Alaska, right on the Ring of Fire. In fact, Kamchatka is kind of known for its volcanoes and not a whole lot else, it seems. Those volcanoes are incredibly active. After all, the Pacific Plate is subducting under the North American Plate along the peninsula, causing an arc of volcanic activity. Wait, Beth, did you say under the North American Plate? Yes. Yes, I did. The North American Plate goes all the way around the Bering Sea. That part of Russia is on the same plate as we are. It's a bit mind-boggling. Anyway, the volcanoes on the peninsula are very active. There are 30 active volcanoes in all, and at the current moment, 8 of them are erupting, including the one involved in our top story today, Shivaluk. Shivaluk has had over 40 violent eruptions in the past 10,000 years. And while the last major blast was in 1964, it has been constantly erupting for more than 20 years now. It's considered the most explosive volcano in the world, and scientists want to understand why. So a team set about to collect what we call primitive magma that have been preserved as small nodules in larger bits of rock that erupted. Kids, do not try this at home. Primitive magma is magma that basically crystallized underground a long time ago and didn't undergo the chemical changes that occurred later in a volcano's life. So the volatile content, all that pressurized gas and liquid, is frozen in time and can tell us about the past conditions underground. If we can figure out what those past conditions were, we might understand what changes happened and use that to predict how other volcanoes may change over time. Seriously, it's amazing what you can learn from tiny crystals in rocks. The team analyzed the minerals in the nodules and found that the water content by weight was in the 10 to 14% range. 8% water is considered superhydrous for subduction zone volcanoes, and 4% is considered average. These results were pretty striking and mean there must have been a lot of water underneath Shivaluk, more so than expected from a magma pool being hydrated by subducted wet rocks. It also means that the magma was at a lower temperature than usual. As co-author Michael Krasinski explained, the only way to get primitive, pristine materials at low temperatures is to add lots and lots of water. Adding water to rock has the same effect as adding salt to ice. You're lowering the melting point. In this case, there is so much water that the temperature is reduced to a point where amphiboles can crystallize. Amphiboles are a set of minerals that form at known pressures and temperatures as magma cools, and they are considered hydrated minerals due to their hydroxide content. These results were published in the journal Contributions to Mineralogy and Petrology and could help us understand how the global water cycle works and possibly even give us some insight into the plumbing system of other volcanoes. After the break, we're going to leave this world and check out a planet 200 light years away. Stay tuned. And now is the time on the Daily Space where we share all that's news in exoplanets and planetary formation theories, which just won't settle down already. We start with the star TOI 178, about 200 light years away. When scientists first observed this star, they initially thought it had 2 planets in orbit at the same distance, which is, of course, unheard of. Yes, we have Lagrange points, but those tend to collect small rocks, not planet-sized masses. Further observations and analysis revealed that this star has not 2, not 3, but 6 planets in orbit around it. And it gets cooler and simultaneously weirder from there. 5 of those 6 planets are in resonance around the star. We see resonance in our own solar system, and I've talked about it before with respect to 3 of Jupiter's Galilean moons. This resonance is where Io orbits Jupiter 4 times for every 2 orbits of Europa and every single orbit of Ganymede. It's like a 3-part harmony, and we call it a 4 to 2 to 1 resonance. Makes sense so far. We've seen resonance in quite a few exoplanetary systems, ranging from 2 to 4 planets. And we've even seen more systems that are in a near resonance, where they're really close to something like 4 to 2 to 1, but it's off by a couple of percent either way for each planet. However, this system presents the first time we've seen a perfect resonance chain with 5 planets, and their ratio turns out to be an 18 to 9 to 6 to 4 to 3 chain. The innermost planet of this chain is the second one from the star, and it goes around 18 times for every 3 times the outermost planet orbits, and it does it in a couple of days. The results will be published in the journal Astronomy and Astrophysics, and co-author Jan Albert explains further. The orbits in this system are very well ordered, which tells us that this system has evolved quite gently since its birth. But then the system gets even more strange, as the compositions of these planets make no sense based on what we know of solar system formation. And I remind you that what we know keeps turning out to be less than we think. Co-author Nathan Hara describes the system. It appears there is a planet as dense as the Earth right next to a very fluffy planet with half the density of Neptune, followed by a planet with the density of Neptune. It is not what we are used to. Once again, a new planetary system has challenged what we think we know. Must be a day ending in Y.
It doesn't even take an entire planetary system to challenge our knowledge of planetary formation. Sometimes all you need is a strange planet. In the case of our next story, that strange planet is WASP 62b, which was discovered back in 2012 but didn't become graduate student Munaz's Alma's project until recently. Alam is doing her thesis on exoplanet characterization, so she looks at known exoplanets and analyzes their atmospheres. Enter WASP 62b, a hot Jupiter about 575 light years away, and half the mass of our own Jupiter, and it only takes 4.5 days to orbit its star. It's extremely hot as a result, and since we have an abundance of hot Jupiters in our exoplanet catalog, likely ignored for that reason as well. In fact, Alam said, "I'll admit that at first I wasn't too excited about this planet, but once I started to take a look at the data, I got excited." The data was spectroscopic observations done with the Hubble Space Telescope, and they showed that sodium was present. Not only was it present, but the absorption lines were complete, meaning no clouds in the atmosphere were present to block the sodium signature. Since less than 7% of studied exoplanets have a clear atmosphere like WASP 62b, this result was surprising. Alam notes that the rarity suggests something else is going on, or they formed in a different way than most planets. Of course, with no clouds, we might be able to use the James Webb Space Telescope to study the composition of the planet itself. And that might help with our pesky planetary formation hypothesis problem.
In more interesting exoplanet news that solves basically nothing, there is a fascinating system some of you may have heard of a time or two, TRAPPIST-1. This system was discovered in 2016 and made headlines for having 7 planets, all similar in size to Earth, and quite a few of them in their star's habitable zone. That made this system an excellent target for planetary scientists and SETI researchers alike. The planetary scientists got tons of telescope time on Kepler and Spitzer in space, as well as TRAPPIST and Speculoos on the ground. Hours and hours of observations were done. And now a new paper published in the Planetary Science Journal looks at the results surrounding the densities of these 7 worlds. Co-author and doctoral student Elsa Ducrot explains, "Our new study has greatly improved the precision of the densities of the planets, the measurements obtained, indicating very similar compositions for these 7 worlds. This could mean that they contain roughly the same proportion of materials that make up most rocky planets, such as iron, oxygen, magnesium, and silicon, which make up our planet. The density of all these worlds turned out to be a about 8% less than Earth, and the team came up with 3 hypotheses on why that is. One hypothesis keeps the composition of the planet similar to Earth, but with 21% iron instead of 32%, which means the core is iron depleted and lower mass than Earth's. The second hypothesis uses rust as the reason for a lower iron content. The planets have vastly more oxygen than Earth, and that oxygen has oxidized the iron all the way through to the core. It's even possible that the density difference is a combination of these two hypotheses. Finally, the third hypothesis gives the planet a water content of 5% the total mass in the outer planets of TRAPPIST-1. These planets are far enough out to still have liquid water, while the inner 3 planets would either have lost their water completely due to the star's heat or had Venus-like atmospheres to prevent the water vapor from escaping. Co-author Carolyn Dorn sums up the work. The TRAPPIST-1 system is fascinating because around this unique star, we can learn about the diversity of rocky planets within a single system. And we can also learn more about a planet by studying its neighbors. So this system is perfect for that. Clearly, more work needs to be done to understand this unusual system, or any system. After the break, we'll move on from the frustrations of planetary formation to galaxies.
One of my favorite things about the universe is that, like a well trained improv actor, its response almost always seems to be yes and. In putting together today's episode, I learned about a new way to form galaxies. In grad school, we were taught that galaxies either form through the bulk collapse of material into massive systems, or through the collapse of material into smaller systems that merged over time into bigger and bigger systems. But in recent years, we've learned there is no or. Both these things are happening, and it's awesome. And today I learned there is yet another possible way to get galaxies. During massive galaxy collisions, streams of material can get torn out of the merging systems, and this debris can form entirely new galaxies called tidal dwarf galaxies, or TDGs. These are new systems made of old material and are capable of star formation. In a new paper in Astronomy and Astrophysics, a team led by Mikel Querjarta uses ALMA to study TGG J1023 plus 1952. Again, do not let astronomers name things. According to co-author Carol Mundell, the little galaxy we've been studying was born in a violent, gas-rich galactic collision and offers us a unique laboratory to study the physics of star formation in extreme environments. The star formation they found wasn't entirely like we're used to seeing in our galaxy. Here, our gas is generally tied up into giant molecular clouds that can collapse into star-forming regions. In this tidal dwarf galaxy, they also found diffuse gas throughout the system. And it's that diffuse gas that's somehow forming stars. And this is another set of ands. Galaxies form through the collapse of material, they form through mergers, and they form from the material discarded in mergers. Stars form in giant molecular clouds. And stars form in diffuse gas permeating these special systems. The science we had was all on track. It just lacked the creativity needed to anticipate all the crazy improv our universe seems ready to do.
This yes and with galaxy mergers was a recurring theme in today's galaxy papers. In a different paper appearing in Nature Astronomy and led by Yohei Miki, researchers modeled what could happen during a variety of different kinds of galaxy mergers, with systems of many different sizes colliding in a variety of ways. This time, the focus was on how gas and dust in the systems moved, and if it would flow towards the galaxy's central massive black holes, or instead get pushed elsewhere. We know that some galaxy mergers do lead to material falling toward the galaxy centers, where it can form a bright disk around the supermassive black hole as it falls in. We can see these systems. We know they're out there. The open question is, does it have to be this way? Do all mergers lead to black holes getting large meals? It turns out if a small galaxy hits a larger galaxy just right, it can actually starve the black hole. Essentially, the interaction shapes the material around the supermassive black hole into a giant donut that the black hole can't munch on. More scientifically, that donut shape is called a torus. And according to Miki, if the incoming galaxy accelerated this torus above a certain threshold determined by properties of the massive black hole, then the matter would be ejected and the massive black hole would be starved. These events can last in the region of 1 million years, though we are still unsure about how long the suppression of massive black hole activity may last. No matter how long it lasts, this is cool science and may even help us understand our galaxy's quiet past. We know we've merged with lots of smaller systems, and we see known evidence of past black hole activity. While we can't go back and see what happened, these simulations may be giving us a hint of our history. After the break, we'll be back with some brain breaking new physics, so stay tuned.
One of the more annoying limiting factors in doing a lot of science is our atmosphere. Place to place variations in temperature, humidity, and other factors lead to the twinkling of stars that we enjoy as children and hate as astronomers. New technologies allowing us to overcome this twinkling in ever more impressive ways. And a recent test of a laser phase stabilization technology allowed Australian researchers to correct for the atmospheric turbulence in 3 dimensions up, down, left, right, and back and forth. This was largely the effort of PhD student Benjamin Dix Matthews, who explains that the technology allowed them to send highly stable laser signals through the atmosphere while retaining the quality of the original signal. It's as if the moving atmosphere has been removed and doesn't exist. This kind of stabilization, once it can be deployed on a regular basis, will allow new kinds of physics experiments to be done. This story caught my attention because it will allow us to actually measure how the ticking of time varies from the surface of our Earth to the orbital distances due to the effects of Einstein's relativity. Beyond enabling new science, these lasers will also be useful for high-speed data transmission. While today's radio waves travel at the same speed of light as these lasers, the lasers can support higher data densities, allowing more information to flow per minute and microsecond. According to co-author Sasha Shidwari, the next generation of big data gathering satellites would be able to get critical information to the ground faster. This new technology was developed to allow the upcoming square kilometer array to synchronize signals between dishes. But once again, it's shown that technology we need to do astronomy can lead to improvements in our fundamental understanding of the universe and breakthroughs in how we communicate around the world. As a reminder, it was researchers in Australia who figured out how to invent Wi-Fi while working on analysis of radio astronomy data.
Using lasers and lights to communicate has long been the stuff of science fiction, and our final story definitely seems straight out of some hopefully not too dystopian sci fi future. Researchers from Nanjing University in China have used drones to transmit photons, light particles, across a kilometer of air and have found they can keep the particles quantum entangled through this journey. Let me try and break this down. If you generate a pair of particles together, they have to balance out a lot of different characteristics, like a matched yin and yang of particle physics. If one of the balanced characteristics in one of the entangled particles changes, somehow the other particle will instantly change to keep things in balance. How this spooky action at a distance works is not understood. But understood or not, folks would like to take advantage of this property to allow instantaneous communications along long distances. In this particular experiment, And the equipment on one drone generated two particles and transmitted one of the particles to another drone and the other particle to a ground station, which relayed the particle to another ground station. Through all of this, the particles stayed entangled. This work is described in the journal Physical Review Letters, and it raises the possibility of drone-enabled quantum networks becoming a real thing someday in the future. Considering how loud drones can be and how much of a hazard they can be for airplanes, I'm not sure if this is something I want to see become our reality. But if Amazon can someday deliver packages with drones, we can also use them to set up particle relay stations. Whatever happens, the future will be weird and awesome and require a lot of quantum mechanics. Thanks for watching. This has been The Daily Space. Tomorrow we'll be back with Rocket Roundup as we bring you updates of what has gone up into space or at least tried to leave our planet Earth.
As a reminder, you can get a complete transcript, show notes, and see images related to each of our stories at our website, dailyspace.org. As a reminder, we are a not for profit educational program, and we're supported by people like you. If you want to become a patron of our show, join us at patreon.com/CosmoQuestX.